Welcome back to ECE 320A. By way of announcements for this video, reminding you to read Chapter 10. At the end of this unit, Unit 1, you need to complete homework number 1. And as a lead-in to Unit 2, at the end of Unit 2, we will be working out, or you will be completing exam number 1, or having exam number 1. In this particular video, I want to talk about the impedance values of resistors, inductors, and capacitors. We'll start with the resistor, then we will use this famous quote, Eli the ICE Man, to remind us about the relationships between voltage and current for inductors, that's Eli, and capacitors, that's ICE, the L and the C, hint, hint. And then we will look at the instantaneous power associated with the inductor and capacitor, again recalling our formula for the instantaneous power that we derived last time for a generic element. Here, when we deal exclusively with a inductor or a capacitor, we'll have a particular relationship between the voltage and current phasors in those individual elements, and that will then simplify or allow some of these parts or three terms in the instantaneous power expression to vanish or be eliminated or removed from that, and we'll be able to see what's happening relative to real power and what we will then call reactive power associated with inductors and capacitors. And then in more general type circuits, meaning ones that might be more inductive or circuits that are more capacitive, they will then act more like an inductor or more like a capacitor, respectively. Let's get started then at looking at these impedance values. And to do that, we'll start with the easiest one, which is the resistor. And now we want to know, how does the resistor vary with frequency, or what is its frequency dependence as a circuit element? And in fact, since a resistor is constant, R, it doesn't have any memory or differential relationship between the voltage and the current. The impedance of a resistor, Z sub R, is just the resistor's value, R. Which means then that if we now look at the voltage-current relationship using Ohm's law, V is equal to IR, we see that R is a constant, so now the current and the voltage are actually in phase. They voltage and current just differ by this resistor value. Or theta sub V is the same as theta sub I, they're in phase, and if we plug that theta sub V value or theta sub I value, those being the same angle, into our average voltage equation, which is VRMS IRMS cosine of theta sub V minus theta sub I, we now have cosine of 0, which is 1, or the average power of a resistor is now the product of the RMS voltage and current. That's the easy one, but it sort of gets us started with this average power associated with these different circuit elements, resistors, inductors, and capacitors. Now let's look or move into Eli the ICE Man. And again, Eli the ICE Man is really just a tool, a mnemonic tool, to allow us to remember relationships concerning with the voltage and current of these two different devices, in particular the inductor for Eli and the capacitor for ICE. Again, Eli, we see that E, the electromotive force, is the voltage. The voltage dropped across an inductor is proportional, or is L. L is the proportionality constant times the time rate of change of the current flowing through that inductor. Likewise, the current through a capacitor, or the induced current, is now proportional to the time rate of change of the voltage across that capacitor. Those are now our time domain relationships between the voltage and the current for the inductor on the left and the capacitor on the right. Now, what we can see in the expression for ELI is that the current, in terms of this equation or formula of ELI, the current comes actually after the voltage in that equation, and in V is equal to L di dt. The current is coming after the voltage. Contrasted with the capacitor, the current comes before. In the word ICE, I comes before E. In the word ELI, E or I comes after the voltage. And now we'll introduce maybe a new term to the way of thinking about after and before. We'll say that the current actually lags the voltage in an inductor because the current comes after, it's lagging behind. So now you can think of a little puppy lagging behind you. If you're now jogging in front of this puppy, now the current lags you, the puppy is behind you. Or in terms of the capacitor, the current leads the voltage in a capacitor. And we'll now use lags and leads a lot during the rest of this semester, or especially in the power portion of this class. And so current lagging the voltage, that means that the current is following in the time domain sense the voltage, and the current leading means that the peak in the current is happening before the peak in the voltage in a capacitor. Let's now use that to relate or find or discover what's going on with respect to the power associated with these reactive elements or these energy storage devices. The inductor is storing energy in the magnetic field, and the capacitor is storing energy in the electric field. And that now introduces some memory into this circuit, and that's because of this differential relationship between the current and the inductor of both of these elements. So now if we look at the inductor, what is the impedance formula for an inductor? And this is from an earlier class, and if you've taken it here, it would be ECE 220, where you looked at sinusoidal steady state behavior, and the impedance formula for an inductor was derived to be J omega L. And you can derive this if you simply look at a current waveform, a sinusoidal, then this J omega L will pop out in front of the formula when you start differentiating that inductor's current. And sometimes we then will write that in terms of reactance, and we'll say J X sub L, and that's a formula, so the reactance X sub L will be omega L. Now, if that's the case, if our inductor has an impedance, it's complex impedance now, it's J omega L, ELI, the current now, reminding ourselves of what we just had, and if I scrolled up just a little, I can give you the answer. The current actually then lags the voltage, the current follows the voltage, and we can now use that insight when as sort of a check on our work relative to this generalization of Ohm's law, which is V, the phasor of our inductor's voltage, is equal to the impedance of the inductor times the inductor's current. If we now put that into phasor form, or identify a magnitude and an angle of both the voltage and the current, we now have V RMS, let's just use RMS units, at an angle of theta sub V, that's the voltage's angle, then the impedance of the inductor is J omega L, and then we have the current of our inductor, which we will now write in polar form as I RMS theta sub I. We now have this relationship, this generalized form of Ohm's law. We can also think of this J omega L. We could write that in polar form. We could say the magnitude of J omega L is now just omega L, and the angle of J omega L is 90 degrees. And where did that 90 degrees come from? You can, in terms of trying to understand some of these concepts or ideas, it's helpful a lot of times to just start sketching. And here is the complex plane. And now we want to know what happens to this complex quantity, J omega L. Well, it is actually in the imaginary direction because we only have one component. It's not a real part plus an imaginary part. It's just the imaginary part. And we're now up here at some location, J times omega L. And omega L just tells us the distance we are along that vertical axis. J actually gives us the direction in, or it tells us we're moving in the imaginary direction. Now, if we looked at the angle of that particular value that I've indicated with a dot, if we look at the angle of that relative to this positive real line, we can see that the angle of that expression, J omega L, is just 90 degrees. If that's the case, then let's now look at the phase in this expression of voltage is equal to Z sub L, I sub L, or we now have, just looking at the phase, we have the angle of the voltage on the left, and on the right we have 90 degrees due to the inductor plus theta sub I of the current. And this now allows us to determine a particular relationship between the voltage and the current. We can now say, if we now simply subtract theta sub I from both sides, we see that for an inductor, the separation or the distance between the angle of the voltage and the angle of the current, theta sub V minus theta sub I, is 90 degrees. We can now use that, remembering our average power formula, and here we're doing for an inductor, that was V RMS, the voltage across that inductor, the current through that inductor, times the cosine of theta sub V minus theta sub I. And we already know what theta sub V minus theta sub I is. That's 90 degrees. And now, if we remember some of the trig information that we should be comfortable with, cosine of 90 degrees, that's actually 0. So now the average power of that inductor is 0, or we have no real power being absorbed by that inductor. And now you might go, well, what's going on, or what's happening? And let's now go back to a little bit more detailed information, or the instantaneous power formula, to see if we can figure out, well, there's current flowing, there's voltage across that inductor. What's going on? Where does the current go, or is there any power, and what's going on? If we look at our instantaneous power expression, and I'll just subscript it with a lowercase l to emphasize that this is now for the inductor, we have 1/2 V max I max cosine of theta sub V minus theta sub I, that's 90 degrees, plus 1/2 V max I max cosine of theta sub V minus theta sub I, that's 90 degrees, cosine of 2 omega t minus 1/2. Remember, we had 3 terms in that instantaneous power formula, minus 1/2 V max I max sine theta sub V minus theta sub I, which is 90, sine of 2 omega t. Again, recalling our knowledge of trigonometry, we now know that the cosine of 90 is appearing in the first two terms, and cosine of 90 is 0. Those first two terms then are gone or disappear, and we're left with the instantaneous power of our inductor due to this voltage and current. The voltage across and the current through is now minus 1/2 V max I max, and we can simplify. Sine of 90 is 1, sine of 2 omega t. And that's now the instantaneous power associated with that inductor. Or we can now make a little bit more knowledgeable assessment of what's going on. The instantaneous power of the inductor what's happening to its variation? Well, now we started with a voltage at a frequency omega and a current with a frequency of omega. Now the power has a frequency of 2 omega. So the instantaneous power of the inductor is twice the frequency of the current and voltage. And what can we say? Well, the instantaneous power just keeps going back and forth. P sub L of t is oscillating. The power, the instantaneous power in this inductor is oscillating, and it's oscillating at twice the frequency of the oscillation in the voltage and the current. Or we could now say that when P sub L of t is positive, we look at the instances in time where P sub L of t is actually positive, and there will be those because it's oscillating around 0. We now say that when it's positive, the energy in that inductor is stored in the magnetic field. So now the energy in that inductor it's energizing the magnetic field of that inductor when the instantaneous power is positive. When the instantaneous power is negative, which it will be for half the time, then the energy in that magnetic field is delivered back to the source. Meaning if we have this inductor in this sinusoidal steady state condition, the magnetic field is expanding and contracting, and as it's doing that, it's absorbing energy and then it gives it off. It's absorbing and releasing, absorbing and releasing. Power companies probably not too happy with us just inflating and deflating, or expanding and contracting, because it's having to deliver that current or supply that current. And for that reason, the power company is probably wanting to keep track, and we are too, because they're going to be charging us for that. We would like to keep track of what's going on, or of this energy. Since in fact the current is actually flowing in the lines that are supplying the power to that inductor, is actually flowing in the lines. And the way that we're going to keep track of that, we can see that we have this expression, and it's actually sinusoidal, and it's now a sine wave of frequency twice of what it was. And let's now use that relationship to define a quantity that's similar to that in form or structure, and we're going to call that now the reactive power, which it will say is Q, and contrast that with the average power, which was P. Remember, the inductor had 0 average power, so we can't measure the average power of the inductor. That's not even there. There is no average power. Instantaneously, there's power flowing back and forth. But now, if we want to talk about steady state expressions, let's now look at something that's in fact orthogonal to the real power, which is Vrms Irms sine of theta sub V minus theta sub I. So because of this sine versus in the real power where we had P, that was VI cosine theta sub V minus theta sub I. This is now 90 degrees or orthogonal to the real power. And we will put the units of this. This won't be watts. This will now be volts, amperes, reactives. Watts is obviously volt amperes, but now we want that unit of the reactive power to be distinct from the real power, and we'll now say that this is volt amperes reactive. And at some point we will start talking about power factor and reactive power. Let's just introduce those for now. And the reactive factor is going to be associated with the sine of theta sub V minus theta sub I, and we'll call that RF. The power factor, so the reactive power is associated with this sine function. The power factor you can anticipate is going to be associated with the cosine factor, and in fact that could be also associated with the average power divided by the magnitude of Vrms Irms, which we will call a different quantity just in a minute, but this is now the cosine of theta sub I minus theta sub cosine of theta sub V minus theta sub I. This expression of the product of the voltage and current in RMS units is what we will call the apparent power, and that's what the power company is having to play with, these magnitudes. That's the apparent power, and now when we take that and divide that into the average power, that gives us a ratio that we will call the power factor. So ideally we would want a power factor close to 1. So the P average we would want to be very close to the apparent power. If that's true, then the difference between theta sub V and theta sub I is very small, which means that the load, we want it to look like it's almost in phase, which is when theta sub V is equal to theta sub I, or we want our load to be as close to real as possible so that we don't have a lot of this reactive power moving through our system. And we can generalize this. This was just for a pure inductor, but if we now looked at a circuit that was more inductive than capacitive, it might have a lot of different inductors and capacitors floating around. But if it's now more tending towards an inductive circuit, then we can say, oh, we have an inductive circuit, ELI is in play, and we now know that the current lags the voltage. Maybe not if it's not a pure inductor, it's not going to lag by 90 degrees, but it's now going to, the current will lag the voltage, which now says that theta sub V minus theta sub I, if the voltage is bigger or is more positive than the current, then if we just called that an angle theta, that angle would be bigger than 0. If we now have a positive angle in the argument of the sign, then Q, VRMS and IRMS are just numbers. Those are the magnitudes of the voltage and current phasor. We have a positive value times the sine of a positive angle. That's going to give us a positive value. Or when we have an inductive circuit, then theta sub V minus theta sub I is positive, or the current lags the voltage. We have Q as positive or non-negative, and we now say that to keep track of that, we can't just say a power factor because that's associated with the cosine, and the cosine will eliminate a sine when we take the cosine of an angle. So now we want to call that a lagging power factor. We can quickly do this same kind of thinking for a capacitive circuit, or in fact, to start with, just a capacitor itself. The impedance of a capacitor is 1 over j omega c. This is now minus j. If we multiplied by j over j, or 1, then we have a minus j scaling 1 over omega c, or we now have minus j, the reactance of that capacitor, x sub c. Again, we have ICE instead of ELI for the capacitor, and here current is in front of the voltage, or the current leads the voltage. And if we now look at the relationship between the current and voltage of a capacitor, we still have this generalized Ohm's law in play. We have V sub C is equal to Z sub C, I sub C. We can look at the phase of the capacitor. We have theta sub V on the left, and the phase of this Z sub C, now we have a J, but we have a minus sign. So if we said J was 90 degrees, now we reverse that, or go 180 degrees from that because of the minus sign. So we now have minus J is now in the lower half of the complex plane, or minus J for Z sub C's angle gives us minus 90 degrees, plus the angle of the current phasor. Or we can now see that if we take and subtract theta sub I from both sides, we now have theta sub V minus theta sub I is minus 90 degrees. And we can now say, oh, this looks similar to what we had with our inductor. If we now look at the average power of this capacitor, we have VRMS, IRMS, cosine, and now we have theta sub V minus theta sub I, which is minus 90. Well, the cosine of minus 90 is the same as the cosine of 90, and that's 0 watts. So that now the instantaneous power of a capacitor is also going to be oscillating. And it's now, if we would go through and replace theta sub V minus theta sub I with minus 90, we would see that we end up with an oscillating P sub C of t. Again, it's oscillating at twice the frequency of the component parts of the voltage and the current, but we still have this oscillation, 0 real power, but now this capacitor's electric field is charging, discharging, charging, discharging, and we can say then that when P sub C of t is positive, then we are storing energy in the electric field of that capacitor. And when it's negative, then the energy is delivered back to the source. Again, we have this instantaneous power that's being oscillating due to this capacitive load or capacitive circuit, and the power company may want to keep track of that. So again, we can think of if we now had a more capacitive circuit than an inductive, again we have ICE, but this now says that the current relative to the voltage is where? Now if we look at ICE, that reminds us that the current is in front of, or it leads the voltage based on ICE. That means then that if we looked at theta sub V minus theta sub I and said that's just an angle theta, what do we know about that? Well, now if the current is bigger than the voltage, this is now going to be something that's negative, and we will say that that now has a leading power factor. And in this case, Q will be negative. So you can maybe anticipate that we will be trying to play the inductor and capacitor off of each other because we're trying to make this angle theta sub V minus theta sub I as small as possible to minimize this extra demand on the system due to inductors and capacitors trying to energize and de-energize their energy storage capacity. And because of that, we will be wanting to maybe introduce a capacitor when we have an inductive load to try to make that angle between the voltage phasor and the current phasor as small as possible.